Targeting cancer signaling pathways by natural products, exploring promising anti-cancer agents. Cancer agents. Shima Hashim Tayyaba Akbar Ali Sabah Akhtar Sabah Nisar Geetanjali Sayyidina Shahid Ali Sherfa Almana Lubna Tharaki Yil Rashid Mir Imad Eldin Elfaqi Mohammad Muzaffar Mir Farooq Jamal Tariq Maisudi Shahabuddin Mayank Singh Mohammad Haris Muzaffar Maka Ajaz A. Bot. Laboratory of Molecular and Metabolic Imaging, Sidram Medicine, Doha, Qatar. B. Keshav Mahavidyalaya, University of Delhi, New Delhi 110034, India. C. International Potato Center, CIP, Shillong, Meghalaya, India. D. Division of Translational Medicine, Research Branch, Sidram Medicine, Doha 26999, Qatar. E. Translational Research Institute, Academic Health System, Hamad Medical Corporation, Doha, Qatar. F. Department of Pharmaceutical Sciences, College of Pharmacy, Qatar University, Doha, Qatar. G. Prince Fahd bin Sultan Research Chair, Department of Medical Lab Technology, FAMS, University of Tabuk, Saudi Arabia. H. Department of Biochemistry, University of Tabuk, Tabuk, Saudi Arabia. I. Department of Basic Medical Sciences, College of Medicine, University of Bisha, Saudi Arabia. J. Dr. Ramanohar Lohia Ovid University, Ayodhya, India. K. Department of Medical Oncology, Dr. B. R. Ambedkar Institute Rotary Cancer Hospital, All India Institute of Medical Sciences, AIIMS, New Delhi, India. L. Laboratory Animal Research Center, Qatar University, Doha 2713, Qatar. M. Center for Advanced Metabolic Imaging in Precision Medicine, Department of Radiology, Perelman School of Medicine at the University of Pennsylvania, Philadelphia, USA. N. Watson Crick Center for Molecular Medicine, Islamic University of Science and Technology, Kashmir, India. Abstract. Cancer is one of the leading causes of death and significantly burdens the healthcare system. Due to its prevalence, there is undoubtedly an unmet need to discover novel anti-cancer drugs. The use of natural products as anti-cancer agents is an acceptable therapeutic approach due to accessibility, applicability, and reduced cytotoxicity. Natural products have been an incomparable source of anti-cancer drugs in the modern era of drug discovery. Along with their derivatives and analogues, natural products play a major role in cancer treatment by modulating the cancer microenvironment and different signaling pathways. These compounds are effective against several signaling pathways, mainly cell death pathways, apoptosis and autophagy, and embryonic developmental pathways, Notch pathway, WNT pathway, and Hedgehog pathway. The historical record of natural products is strong, but there is a need to investigate the current role of natural products in the discovery and development of cancer drugs and determine the possibility of natural products being an important source of future therapeutic agents. Many target-specific anti-cancer drugs failed to provide successful results, which accounts for a need to investigate natural products with multi-target characteristics to achieve better outcomes. The potential of natural products to be promising novel compounds for cancer treatment makes them an important area of research. This review explores the significance of natural products in inhibiting the various signaling pathways that serve as drivers of carcinogenesis and thus pave the way for developing and discovering anti-cancer drugs. Introduction. Despite the development of various treatment strategies, cancer remains a major cause of death worldwide. 2. Cancer is generally described as a pathological condition characterized by uncontrolled growth and proliferation of cells due to the accumulation of genetic mutations. 3. 4. Cancer's incidence and mortality rate rise exponentially, with 19.3 million new cancer cases and approximately 10 million deaths in 2025. Cancer is commonly treated using conventional treatments such as radiotherapy, chemotherapy, and surgical removal. However, cells' resistance to these therapies reduces their effectiveness. 1. The increasing incidence of deaths due to cancer requires the development of therapeutic approaches that pose lower cytotoxic side effects and resistance. Natural compounds exhibit various beneficial activities that include improving health and treatment of cancer. Natural products are naturally occurring compounds that possess biological activities derived from abundant natural resources such as plants. Many currently used therapeutic drugs are derived from natural resources such as alkaloids, taxanes, and flavonoids. 6. Recently, chemotherapy using natural compounds has gained increased attention to improve the therapeutic index of specific antineoplastic drugs. 7. Moreover, cancer treatment by natural compounds, including phytochemicals, minerals, and vitamins, has shown promising results against various malignant tumors. 8. 9. In this regard, natural compounds with potent anti-tumor activity and minimum toxicity in healthy tissues have been suggested to study their synergistic efficacy with traditional anti-cancer drugs. 10. 11. Natural products have displayed selective benefits against cancer cells compared to normal cells, but their chemical structures also act as models for developing novel drugs. These models formulate drugs with similar or better benefits than existing natural products with lower side effects and resistance. 12. One such interesting option is chemoenzymatic biotransformation, which uses common natural products as substrates to generate chemically diverse and well-characterized libraries of natural product derivatives. 13. There have been several modifications to this tool, and one among them is using the secretome, blend of enzymes, of specific fungi instead of using an intact microorganism or a pure enzyme to obtain chemically diverse natural product derivatives. 14. The utilization of secretome takes the use of diverse enzymes catalytic promiscuity. 15. This technology has been successfully used to generate specific libraries of stilbene dimers. 16, 17, and phenylpropanoids. 14. Phenylpropanoids as secondary metabolites have been shown to possess anti-cancer properties by virtue of their potential antioxidant activities. 14, 18, 19. Phenylpropanoid derivatives such as caffeic and ferulic acids represent important substrates as relevant building blocks in drug discovery. 20, 21. Previous research has shown that using these molecules as the starting material for the biotransformation of more complicated compounds using a purified enzyme has been successful. Previous studies have demonstrated the successful use of these compounds as the starting material for the generation of more complex compounds through a biotransformation process using a purified enzyme. 22, 23. Therefore, natural products and their derivatives could be better chemotherapeutic agents due to their high selectivity, reduced cost, and low toxicity. 24. Various cell signaling pathways are altered in different tumor types. Cellular signaling pathways are complex and interconnected communication networks of interacting molecules that regulate the biological activities of the cells. 25. Cells receive information from different growth factor receptors and integrate this information to regulate different cellular processes such as cell proliferation, cell death, protein synthesis, cell motility, differentiation, cell architecture, and polarity. 26. Signaling pathways regulate cellular development and bring about different changes in different cell types. Multiple signaling pathways regulate cell survival, proliferation, and motility. Therefore, cancer cells can proliferate through an alternative signaling pathway when a mutationally activated pathway is blocked by an inhibitor. 26. Thus, an advanced treatment for cancer requires effective combination therapies such as signaling inhibitors or a combination of signaling inhibitors with DNA-damaging chemotherapeutic agents. 27. Therefore, understanding the intricacy of these pathways is essential for studying tumor cell behavior. Several pathways have been identified to be frequently altered in cancer, such as the cell cycle pathway, Pi3K/ANITE, and RAS/MAP kinase pathways. 28. In addition, aberrations in the WNT/beta-catenin signaling have also been observed across different tumor types. 29, 30, 31. Despite having vast knowledge of the molecular mechanism of these cancer-associated cellular signaling pathways, the chemotherapeutic approaches targeting the oncogenic biomarkers are limited. 28. Therefore, A thorough understanding of the changes in cell signaling pathways is essential to identify potential therapeutic targets. Many natural compounds have shown numerous anti-cancer activities in different cancer types. Therefore, this review will discuss the comprehensive function of some major natural compounds in various cancers. Additionally, Table 1 discusses additional natural compounds with their role in cancer prevention besides the important ones that have been reviewed extensively here. Table 1. Comprehensive list of natural compounds with their associated anti-cancer activities. Natural compound source type of cancer outcome reference, S. Formononedin red clover gastric cancer. Inhibition of cell proliferation in MGC803 cells. Inhibition of the migration in SGC7901 tumor cells via WNT/beta-catenin and ANITE/mTOR pathway. 166, 167. Onyx shawl magnolia officinalis magnoliaceae colon cancer, oral cancer, thyroid cancer. Recruitment of JAGID1 and HES1 towards downstream gene target. Downregulation of CSC marker DCLK1. Downregulation of CD44 and WNT/beta-catenin, SP, receptor inhibitor. 168, 169. Curcumin turmeric colon cancer, gastric cancer, AML, breast cancer, head and neck cancer, lung cancer. Reduction of CD44 and CD166 expression in chemoresistant colon cancer. Inhibition of tumor growth of ALDH+/CD133+ cells. Downregulation of GLI1, NOTCH1, and cyclin D1. Downregulation of the mRNA and the protein expression of cyclin D1. 170, 171, 172. Ursolic acid and coeat-japic acid apples, pears, and prunes colon cancer. Inhibition of STAT3 phosphorylation and induction of caspase-3 cleavage in ALDH, /CD133, colon cancer initiating cells. 173. Hesperidin citrus fruits non-small cell lung carcinoma. Modulation of NF-kappa B signal transduction thereby mediating growth inhibition through apoptosis. 174. Isobutyrophenone and arnicolide centipeda minima, L. A. Braun and Ash. Composite colon cancer. Promotion of intracellular ROS production. Downregulation of NF-kappa B protein. 175. Epigallocatechin gallate green tea skin cancer. Inhibition of PKD1 activation. 176, 177. Gossipole cotton plants prostate cancer. DNA damage induction, activation of P53, and induction of apoptosis. 178, 179. Ethoxymansonon G. mansonia gagi ij.r. Drum. Malvaceae breast cancer. Inhibition of estrogen-induced cell proliferation. 180. Jenny Stein soybeans and soy products prostate cancer, cervical cancer, colorectal cancer, non-small cell lung carcinoma. Inhibition of Hedgehog GLI signaling and expression of CSC markers CD44. P53 stabilization through APE1 pathway. Inhibition of ANITE pathway. 181, 182. Sulforaphane cruciferous vegetables prostate and pancreatic cancer. Induction of apoptosis and inhibition of self-renewing potential, ALDH1 activity, carcinogenicity, xenograft growth in pancreatic CSCs. Enhanced drug cytotoxicity when combined with other conventional drugs in prostate CSCs. Inhibited relapse of gemcitabine-treated tumor cells in nude mice. 183. Proanthocyanidins grape seeds pancreatic adenocarcinoma. Reduction of NF-kappa B expression and reversal of the epithelial mesenchymal transition process. 184, 185. Methylanthcenate A antradiacamphorate breast cancer. Downregulation of heat shock protein 27. Upregulation of ICP and P53 expression. 186, 187. Oridinin rhabduggia sens lamiaceae breast cancer. Downregulation of JAGAD2 expression and NOTCH1 activity. Activation of the PI3K/PTEN/anite/mTORC1 and WNT/beta-catenin pathways. 188, 189. Resveratrol grapes head and neck cancer, gastric cancer, thyroid cancer, lung cancer. Downregulation of ALDH1 and CD44 in HNC ticks in a dose-dependent manner. 190, 191, 192. Gugglesterone commiforum mucol, hook. X stocks, English. Bursaceae colon cancer, prostate cancer, head and neck cancer. Activation of caspase-9, caspase-8, and caspase-3. Induction of cell death in PC3 cells. Induction of apoptosis in HT29 cells by activating caspases 3 and 8. Downregulation of CIAP1, CIAP2, and BCL2 levels and upregulation of truncated BID, FOS, PJNK, and PC-Jun. 193, 194, 195. Emidin rhubarb prostate cancer. Activation of Notch signaling pathway. 196. Artesunate artemisia annua compositae chronic myeloid leukemia. Inhibition of VEGF expression. 197. Allicin garlic ovarian cancer. Activation of JNK pathway. 198. Caffeic acid phenethyl ester, CAPE, propolis of honeybee hives prostate cancer. Induction of cell G1 or G2/M cell cycle arrest. 199. Erinacin A, dithyrpenoid, Hericium erinaceum gastrointestinal cancer, colorectal cancer. ROS-mediated cell cycle arrest. Attenuation of NF-kappa B activity in cancer stem cells. 200, 201. Morris alba L. Moraceae cervical cancer. Downregulation of the PI3K/anite/mTOR pathway. 202. Deoxychiconin arnebia euchroma boraginaceae colorectal cancer, glioma. Growth inhibition and apoptosis induction by modulating BCL2, BAX, and STAT3 proteins. 203, 204. Apigenin scutellariae SPP colorectal cancer, lung cancer, osteocarcinoma, liver cancer, melanoma, prostate cancer. Induction of cell cycle arrest at G2/M phase. Promotion of different anti-inflammatory pathways, including P38/MAPK and PI3K/anite. Alteration of RAF1 kinase mediating apoptosis. 205, 206, 207, 208. Paclitaxel Pacific utree endometrial cancer, sarcoma, cervical cancer, gastroesophageal cancer, prostate cancer, head and neck cancer. Activation of MEK-independent signaling pathway. 209, 210. Tannin/tannic acid syzygium guineans gallnuts triple-negative breast cancer. Colon cancer, lung cancer, liver cancer, ovarian cancer, prostate cancer, pancreatic cancer. Embryonic carcinoma. Inhibits cell proliferation via WNT3A-induced beta-catenin. Downregulate JAK/STAT pathway. Inhibit cell cycle progression by G1/S phase arrest. Decrease TGF-beta-induced EMT and NF-kappa B activation. Acts synergistic with cisplatin and oxaliplatin. Promotes trail-induced extrinsic apoptosis. 211, 212, 213. Caloropin asclepiadoidea family colon cancer. Inhibits beta-catenin. 214. Quercetin nuts, tea, onions, apple, and in plant sources colorectal cancer, triple-negative breast cancer. Inhibits phosphorylation of GSK3-beta. Upregulate E-cadherin. 215. Lycopene red fruits and vegetables prostate cancer. Decrease cyclin E expression. Inhibits beta-catenin. Inhibits phosphorylation of GSK3 beta. 215. Abbreviations: WNT, wingless related integration site, beta-catenin, anite, protein kinase B, mTOR, mechanistic target of rapamycin, CSC, cancer stem cell, DCLK1, double cordon-like kinase 1, cluster of differentiation 44, cluster of differentiation 166, ALDH, aldehyde dehydrogenase, CD133, cluster of differentiation 133, GLI1, GLI family zinc finger 1, Notch 1, Notch receptor 1, STAT3, signal transducer and activator of transcription 3, NF-kappa B, nuclear factor kappa B, ROS, reactive. Oxygen species, PKD1, polycystin 1, APE1, apurinic/apyrimidinic endonuclease 1, ALDH1, aldehyde dehydrogenase 1, ICP, I-kappa B alpha, PI3K, phosphoinositide 3 kinases, PTEN, phosphatase and tensin homolog, mTORC1, mammalian target of rapamycin complex 1, HNC-TIX, head and neck cancer-derived tumor-initiating cells, CIAP1, cellular inhibitor of apoptosis protein 1, CIAP2, cellular inhibitor of apoptosis protein 2, BCL2, B-cell lymphoma 2, BID, BH3 interacting domain death agonist, FOS, cell surface death receptor, PJNK, phosphojune nuclear kinase, PCJune, phosphorylated C-june, VEGF, vascular endothelial growth factor, JNK, June nuclear kinase, BAX, BCL2 associated X, apoptosis regulator, P38/MAPK, P38 mitogen activated protein kinase, MEK, mitogen activated protein kinase, TGF-beta, transforming growth factor beta, EMT, epithelial to mesenchymal transition, TRAIL, tumor necrosis factor related apoptosis inducing ligand, GSK3 beta, glycogen synthase kinase 3 beta. 2. Targeting signaling pathways by natural products. Natural compounds can target various signaling pathways, thus impacting the molecular activity of cells. Consequently, they can be used as potential adjuvants in cancer therapy. Significant advancements have been made in treating malignant tumors through surgery, chemotherapy, and radiotherapy. However, the development of invasive or diffuse cancers is often associated with poor patient diagnosis and remains a major obstacle in cancer treatment. 32. Latest studies show that cancer stem cells, CSCs, capable of initiating tumor and self-renewal, are responsible for tumor relapse and resistance to chemotherapeutic treatment. 33, 34, 35. Thus an elevated CSCs population leads to poor patient prognosis and ineffectiveness of multiple anti-cancer treatments. Fig. 1. The following sections highlight the importance of various natural compounds in targeting aberrated cell signaling pathways in cancer. Fig. 2. Fig. 1. Download high-res image, 191 KB. Download full-size image. Fig. 1. Role of natural products in cancer prevention. The utilization of natural compounds as adjuvant therapy in targeting the cancer cell's apoptotic pathways and as a solo therapy to inhibit cancer cells' self-renewal pathways, HH, Notch, WNT and BMI1, subsequently inhibiting the tumor relapse and resistance to chemotherapeutic drugs. HH, Hedgehog, WNT, wingless related integration site, BMI1, B lymphoma MOMLV insertion region 1 homolog. Fig. 2. Download high-res image, 291 KB. Download full-size image. Fig. 2. Schematic representation of natural compounds targeting cancer signaling pathways. Onyxol exerts anti-cancer properties by inhibiting SOS binding with RAS, thus suppressing RAS activation, thereby inhibiting RAL and PDL. Inhibition of PDL does not allow binding of PAR, resulting in mTOR suppression while increasing BAD expression. Apigenin increases the PTEN expression, and like paclitaxel and curcumin inhibits the activity of FOP3K, which subsequently inhibits the expression of phosphoanite that upregulates BAX and downregulate BCL2, leading to the mitochondrial membrane damage and release of AFE. Curcumin also inhibits the IL-6-induced JAK2/STAT3 pathway. Additionally, curcumin impedes WNT signaling, and capsaicin inhibits STAT activation, thus phosphorylating beta-catenin, which hinders its entry into the nucleus along with STAT. Phosphorylated beta-catenin does not allow c-Myc to stimulate cyclin D1. Resveratrol increases the activity of GSK3, which causes downregulation of SNAIL, N-cadherin, and vimentin, while upregulates E-cadherin. This results in the inhibition of EMT transition. All of these pathways either cause cancer cells apoptosis or inhibits proliferation and metastasis and invasion. SOS, son of 7-less, guanosine nucleotide exchange factors, RAS, rat sarcoma virus, RAL, RAS-like, PDL, phospholipase D, mTOR mechanistic target of rapamycin, PA phosphatidic acid, BAD, BCL2 associated agonist of cell death, PI3K, phosphatidylinositol 3 kinase, ANITE, protein kinase B, PTEN, phosphatase and tensin homolog, IL-6, interleukin-6, BAX, BCL2 associated X protein, BCL2, B-cell lymphoma 2, AFE, apoptosis inducing factor, JAK2, Janus kinase 2, STAT signal transducer and activator of transcription, WNT, wingless related integration site, c-Myc, cellular myelocytomatosis, GSK3, glycogen synthase kinase 3, N-cadherin, neural cadherin, E-cadherin, epithelial cadherin, EMT epithelial mesenchymal transition. 2.1. Onyxol. Onyxol is a natural phenolic cytotoxic compound produced by Magnolia grandiflora L. Magnoliaceae and is used in traditional medicines in most Asian countries. 36. Onyxol exhibits anti-inflammatory, anti-angiogenic, antioxidative, and anti-tumor activities. 37, 38. It has been reported to suppress the expression of cyclooxygenase 2, prostaglandin E2, proliferating cell nuclear antigen and tumor necrosis factor alpha, interleukin, IL-1 beta, and IL-6 in skin cancer. 39. Moreover, Onyxol treatment induced apoptosis in SKH1 mice in which skin tumor was induced through UVB. The apoptosis in skin cancer was facilitated through the activation of p53, DNA fragmentation, caspase activation, and poly-adenosine 5-diphosphate ribose, polymerase, PARP, cleavage. 39. Onyxol has also been reported to exhibit anti-cancer properties in breast cancer. 37, 40. In triple-negative breast cancer cell line, MDA-MB231, Onyxol inhibited phospholipase D and RAS activation. 37, 40. It also inhibited nuclear factor kappa B, NFKB, COX-2, prostaglandin E2, and cellular signaling mediated by SRC/epidermal growth factor receptor. 37. Recently, Onyxol has been found to sensitize breast cancer cells to doxorubicin by downregulating the expression of miR-188.5P via FBXW7/c-Myc signaling. 41. In addition to breast cancer, Onyxol has also displayed anti-cancer activities in ovarian cancer, as it was found to induce apoptosis in ovarian cancer cells through the activation of caspases and cleavage of PARP. Moreover, treatment with Onyxol resulted in the accumulation of ovarian cancer cells in the sub-G0/G1 phase. 37, 42. It has also been reported that Onyxol exerts its anti-cancer properties in ovarian cancer through the AMP-activated protein kinase/mechanistic target of rapamycin, AMPK/mTOR, signaling pathway, as it activates AMPK and reduces the phosphorylation of mTOR in ovarian cancer cells. 42. Onyxol has also been implicated in preventing and treating prostate cancer. 43. Onyx-Schall-induced DNA fragmentation and apoptosis in prostate cancer cells irrespective of androgen or p53 status 44. The apoptosis in prostate cancer cells was induced by reducing anti-apoptotic proteins and inducing pro-apoptotic proteins 44. In addition, Onyx-Schall has also been reported to display anti-neoplastic effects in gastric cancer by reducing cyclooxygenase 2, COX-2, and peroxisome proliferator activated receptor gamma, PPAR gamma, which are found to be involved in tumor growth, and increasing the expression of 15-LOX1 in gastric cancer cells 37, 45. Onyx-Schall also induced apoptosis in gastric cancer cells by inducing calcium-dependent thiol proteases, caspase-7, 12 activations and reducing glucose-regulated protein, GRP94, expression 46. Additionally, Onyx-Schall has displayed anti-cancer effects in renal cancer through the downregulation of c-Met and phosphorylated RAS in renal cancer cells. Moreover, Onyx-Schall was found to induce apoptosis and reduce blood vasculatures in renal cancer cells 47. 2.2. Paclitaxel. Paclitaxel, Taxol trademark, is produced in the needles and bark of Taxus brevifolia nut. Taxaceae and has been reported to exhibit antineoplastic properties 48, 49. It belongs to a class of taxane drugs and is widely used as a natural anti-cancer compound 48, 49. Paclitaxel exerts anti-cancer effects by binding to tubulin and promoting its assembly into microtubules. It prevents the dissociation of microtubules and thus blocks cell progression and eventually prevents the growth of cancer cells 50. Paclitaxel has been reported to be involved in many signal transduction pathways that may be associated with its apoptotic promoting properties. In breast cancer cells, paclitaxel induce apoptosis by activating ERK, p53, and p38 MAP kinase 51. Moreover, paclitaxel also displayed anti-cancer effects through various signaling pathways such as toll-like receptor 4-dependent pathway, Janus kinase, JAK, signal transducer and activator of transcription factor pathway, and NFKB in breast cancer 51, 52, 53, 54, and through c-Jun N-terminal kinase, CJNK, stress-activated protein kinase, SAPK, in ovarian cancer 55. Paclitaxel has been found to inhibit the cell proliferation of canine mammary carcinoma cell lines and cause cell cycle arrest at G2/M phase 56. Paclitaxel-mediated apoptosis through the upregulation of p53, BAX, and cleaved caspase-3 and the downregulation of BCL2 in canine mammary carcinoma cell line cells 56. Moreover, treatment with paclitaxel reduced the expression of p-anite and pp70s6k and increased the expression of pp38 and pp90rsk in canine mammary carcinoma cell line cells 56. Upon combination with tanghinone I, a natural compound derived from Chinese herbal medicine, paclitaxel induced apoptosis in human ovarian cancer cells, A2780, and mouse ID8 cells through the upregulation of BAX and downregulation of BCL257. Another study showed that the combination of paclitaxel with lobaplatin reduced the expression of p-anite and phosphoglycogen synthase kinase 3-beta, PGSK3-beta, and inhibited the Pi3K/anite signaling pathway in lung cancer cells, NCIH446, 58. In another study, paclitaxel was found to reduce the proliferation of non-small cell lung carcinoma cell line A549 through the upregulation of P53 and MEG359. Though paclitaxel has several advantages, whether used alone or in conjunction with anthracyclines 60, 61 to treat breast cancer, it does have certain drawbacks, such as being poorly soluble in water due to hydrophobic characteristics, necessitating the use of solvents in clinical formulations. Solvents used as carriers in these formulations cause severe toxicity and can limit the amount of drug delivered to tumors 62. To address these limitations, the FDA recently approved nanoparticle albumin-bound paclitaxel, nab-paclitaxel, marketed as a Braxane-registered trademark, a solvent-free version of paclitaxel, for the treatment of metastatic breast cancer, citing greater anti-cancer efficacy and tolerability over solvent-based paclitaxel 62, 63, 64, 65, 66. The inherent capabilities of albumin are used by nab-paclitaxel to reversibly bind paclitaxel, transport it through the endothelial cell, and concentrate it in tumor regions. Glycoprotein 60-mediated endothelial cell transcytosis of paclitaxel-bound albumin and accumulation in the tumor by albumin binding to SPARC, secreted protein, acidic and rich in cysteine, is part of the hypothesized drug delivery mechanism 62, 67. Clinical trials have demonstrated that nab-paclitaxel is more effective than paclitaxel manufactured as Crema-4L, CREL, Taxol, CRL-paclitaxel, in second-line patients, with nearly double the response rate, longer time to disease progression, and higher survival 68, 69. 2.3. Capsaicin. Capsaicin is an anti-tumor vonoloid compound derived from the genus Capsicum 70. It has been reported to induce apoptosis via the caspase-independent pathway and through suppression of proto-oncogene, FBI1-mediated NFKB in breast cancer cells 70, 71. Moreover, in breast cancer, it reduced expression of BCL2, survivin, and Ki67 in vivo and in vitro, whereas it increased the expression of BAX and activated caspase-372. In triple-negative breast cancer cell line, MDA-MB231, capsaicin has been shown to decrease the expression of cyclin-dependent kinase 8, CDK8, reduce cancer cell viability, and induce cell cycle arrest in the G2/M phase 72. Moreover, capsaicin has been reported to inhibit breast cancer cell viability by downregulating the CDK8/Pi3K/anite and inhibiting the WNT/beta-catenin signaling pathway 72. Besides breast cancer, capsaicin also exhibits anti-cancer properties in esophageal squamous cell carcinoma, where it decreased the expression of matrix metalloproteinase 9, MMP9, EMP-activated protein kinase, and nuclear factor Cap-Ab, NF-kappa-B, 73, 74. In gastric cancer cells, capsaicin induced apoptosis via the modulation of the mitogen-activated protein kinase, MAPK, signaling pathway 75. In colon cancer, capsaicin has been reported to elicit anti-cancer activity through the degradation of cyclin D1 and inactivation of 20S proteasome 74, 76. Moreover, it has been reported that capsaicin exerts its anti-cancer effects in prostate cancer through the suppression of the WNT/beta-catenin pathway 77. It inhibited PGSK3-beta, WNT2, beta-catenin, cyclin D1, and c-MYC in prostate CSCs 77. In addition, capsaicin has been reported to suppress pancreatic cancer cell proliferation by inhibiting Hedgehog, extracellular signal-regulated kinase, and c-Jun signaling pathways 78. Moreover, capsaicin inhibited proliferation and induced autophagy, apoptosis, and cell cycle arrest at the G1 phase in NPC cells. 79. In addition, treatment with capsaicin was found to inhibit the phosphorylation of anite, mTOR, ERK, and PGSK3-beta and reduce the expression of PI3K in NPC cells, suggesting that capsaicin exerts anti-cancer effects by downregulating the PI3K/anite/mTOR signaling pathway. In another study, treatment with capsaicin was found to decrease cell viability and inhibit proliferation in osteosarcoma cells. In addition, the study reported the involvement of the mitochondrial apoptotic pathway in the capsaicin-induced apoptosis in osteosarcoma cells 80. Moreover, the study reported that the anti-cancer effects exerted by capsaicin involve the MAPK signaling pathways 80. 2.4. Resveratrol. Resveratrol, Res, 3,4,5-trihydroxystilbene, is a non-flavonoid phytoalexin compound derived from plant species including grapes, peanuts, plums, and berries 81. However, increased levels of residential exist in the plant Polygonum cuspidatum polygonaceae and Vitis rotundifolia mix. Vitaceae 82. Residential has been reported to inhibit cell proliferation and induce mitochondrial-mediated and caspase-independent apoptosis in transgenic adenocarcinoma of mouse prostate, TRAMP, cells. It was shown that residential exerted its anti-cancer effects through changes in the expression of BAX/BCL2 and disturbance of the mitochondrial membrane potential in TRAMP cells 82, 83. Although residential is shown to be an effective anti-tumor agent, its application is limited due to low aqueous solubility and poor bioavailability. To overcome these limitations, various nanodelivery systems such as polymeric nanoparticles, lipid nanoparticles, liposomes, micelle, lipid nanoparticles, gold and silver nanoparticles, and silica nanoparticles for residential loading have been utilized. Detailed review in 84, 85, 86. These nanostructures and nanoformulations have distinct physicochemical qualities, such as high loading capacity, cargo protection, and deep tumor penetration, in addition to better safety and biocompatibility. Liposomes are one of the earliest lipid-based drug nanocarriers that have been thoroughly studied, mainly consisting of phospholipids and cholesterol with an inner hydrophilic core and an outer hydrophobic lipid bilayer 87. This molecular organization of the liposomes enables efficient delivery and enhances the drug's effectiveness. Using the same technique, a study evaluated the efficiency of liposomal encapsulated residential to treat breast tumors in a mouse model. The study found that the encapsulated residential inhibited tumor growth effectively at a reduced dosage with no cytotoxicity to normal tissues. In addition, the encapsulated residential induced apoptosis in breast tumors by upregulating the expression of tumor suppressor p53, downregulating the expression of anti-apoptotic protein BCL2, and inducing caspase-3 activation. 88. It has also been shown that residential exerts anti-cancer effects through neutralizing reactive oxygen species, ROS, and inhibiting MMP9 in mouse breast cancer cells in vitro and in vivo 82, 89. Another study showed that residential inhibited the cell proliferation migration and invasion of renal carcinoma cells via the inactivation of ANITE and ERK1/2 signaling pathways. Moreover, the study found that residential suppressed the mesenchymal markers such American Samoa vimentin, N-cadherin, and snail and increased the expression of epithelial marker E-cadherin, thus demonstrating its role in reversing epithelial to mesenchymal transition, EMT, in renal carcinoma cells 82, 90. A study showed the synergistic effect of residential endocetaxel in prostate cancer cell lines, C42b and DO145. The combination treatment promoted apoptosis in prostate cancer cells by upregulating the pro-apoptotic genes and downregulating the anti-apoptotic genes. Moreover, the combination treatment upregulated the expression of tumor suppressor p53 and cell cycle inhibitors such as p21 and p27, resulting in cell cycle arrest at the G2/M phase 91. Residential has also been shown to exhibit anti-proliferative effects in osteosarcoma cells by inhibiting the expression of endothelial growth factor, VEGF, 82, 92. Residential induced apoptosis in osteosarcoma cells through caspase-3 activation, cleavage of PARP, upregulation of BAX, and downregulation of BCL2 and BCLXL. Moreover, it reduced the phosphorylation of Janus kinase 2, JAK2, signal transducer and activator of transcription 3, STAT3, and inhibited the expression of PPi3K, PNite, and NF-kappa B in osteosarcoma cells 93. In colorectal cancer-derived cell lines, residential inhibited metastasis and cell invasion through the inhibition of the WNT/beta-catenin signaling pathway 82, 94. Residential reversed EMT through the ANITE/GSK3 beta/snail signaling pathway in colon cancer cells and tumor tissues of nude mice. Treatment with residential increased the expression of epithelial marker E-cadherin and decreased the expression of mesenchymal markers such as N-cadherin and snail 95. In another study, residential inhibited cell proliferation-induced apoptosis and cell cycle arrest at the G1 phase in colon cancer cells. In addition, the study identified AKT1 and AKT2 as potential targets of RES. Furthermore, the study found that ANIT1/2 knockdown inhibited cell proliferation and colony formation in colon cancer cells, effects that were similar to those caused by residential treatment. 96. 2.5. Apigenin. Apigenin is a natural trihydroxyflavone found in various fruits, vegetables, and nuts. It exhibits significant physiological and pharmacological properties, including anticancer, antioxidant, antibacterial, and antiviral properties. 97. The anticancer effect of apigenin has been observed in several cancers, including colorectal cancer. 98, 99, melanoma, prostate cancer, lung cancer, osteosarcoma, liver cancer, and breast cancer. 100, 101. Apigenin exerts its anticancer effects by inhibiting several signaling pathways, inducing apoptosis, autophagy, cell cycle arrest. 122, and inhibiting cell migration and invasion. 102. Studies demonstrate that apigenin is associated with the modulation of many cell signaling pathways such as WNT/beta-catenin. 99, 103, JAK/STAT. 101, AMPK. 104, TGF-beta. 105, and FAK/ERK1/2. 106. Apigenin is also found to exert immune regulatory activities in an organic-specific manner by modulating NF-kappa B activity in the lungs of transgenic mice. 107. A study showed that CO treatment of apigenin with cisplatin enhanced the cytotoxic effect of cisplatin in multiple cell lines, MCF7, HeLa, A549, and HCT116. In addition, apigenin was found to induce apoptosis in human lung cancer A549 cells through the ERK/MAPK pathway activation. Moreover, the combination treatment with apigenin and cisplatin-induced caspase-dependent apoptosis in A549 cells elevated the expression of p53 and promoted p53 phosphorylation and accumulation in A549 cells. 108. Previous studies have reported that progestins, a medication that mimics the effects of naturally occurring female sex hormone progesterone, favor breast cancer metastasis or could be a risk factor for developing breast cancer in women who consume progestins. 109, 110. Given this, a study demonstrated the effect of apigenin on the growth of BT474 xenograft tumors in nude mice exposed to progestin, medroxyprogesterone acetate. 111. The study found that apigenin effectively inhibited the progression of the xenograft tumors by inhibiting proliferation, inducing apoptosis, and reducing the expression of proto-oncogene HER2/neu. 111. Additionally, apigenin was also found to reduce VEGF levels, thereby inhibiting cell survival. 111. Another study showed that apigenin inhibited cell proliferation and induced autophagy by suppressing the Pi3K/ANIT/mTOR signaling pathway in hepatocellular carcinoma in vitro and in vivo. 112. Furthermore, cervical cancer HeLa cells treatment with apigenin 7-O-glucoside, AGL, inhibited cell proliferation, induced cell cycle arrest at G0/G1 phase, reduced mitochondrial membrane potential, and increased the expression of pro-apoptotic proteins and downregulated anti-apoptotic proteins in. 113. Moreover, the study found that AGL promoted apoptosis in cervical cancer cells via the PTEN/ANIT/Pi3K pathway. 113. EMT is an important process in the metastasis of colorectal cancer. Targeting EMT using natural products and dietary compounds has gained much attention during the past few decades. Apigenin has been found to reverse EMT in colon cancer cells by upregulating the expression of E-cadherin and downregulating the expression of SNAIL. Moreover, apigenin inhibited the expression of NF-κB and reduced the transcriptional activity of SNAIL, thus demonstrating that apigenin reversed EMT via suppressing the NF-κB/SNAIL pathway. 114. Another study showed that apigenin induced apoptosis and autophagy in cisplatin-resistant HT29 colon cancer cells by inhibiting the mTOR/Pi3K/ANIT signaling pathway. 115. 2.6. Curcumin. Curcumin, also known as diferuloylmethane, is a primary component of turmeric. Curcumin interacts with various cellular targets and, therefore, is regarded as a pleiotropic molecule 116-117. Many studies have investigated the effectiveness of curcumin in various pathological processes such as inflammation, infection, hepatic diseases, cancer, and diabetes 118. Several in vivo studies have demonstrated the pro-apoptotic effects of curcumin. Curcumin inhibited tumor growth in nude mice, which was injected with tumor spheres of lung cancer NCIH460 cells. Curcumin was found to repress NCIH460 tumor spheres via suppressing the JAK2/STAT3 signaling pathway 119. JAK2/STAT3 pathway activity is constitutive in cancer cells and is involved in various cancer initiation processes 120. Thus, JAK2/STAT3 pathway is a great target for curcumin to suppress tumor formation. In another study, curcumin inhibited cell proliferation and induced caspase-dependent apoptosis in a dose-dependent manner via JAK/STAT3 pathway suppression in primary effusion lymphoma cells 121. Studies suggest that IL-6 promotes proliferation and survival of multiple myeloma cells through STAT3 phosphorylation. Thus, agents that suppress STAT3 phosphorylation, such as curcumin, are potential therapeutic targets for treating multiple myeloma. Treatment with curcumin was found to inhibit constitutive STAT3 phosphorylation and proliferation in multiple myeloma cells 122. Interestingly, curcumin emerged as a much stronger inhibitor of STAT3 phosphorylation than AG490, a selective inhibitor of the Janus kinase 2, JAK2/STAT3 signaling pathway 123. Moreover, in other cancer cell lines such as pancreatic 124, 125, ovarian and endometrial 126, 127, malignant gliomas 128, 129, and hepatocellular 130, curcumin was also reported to inhibit cellular proliferation by downregulating the JAK-STAT3 signaling pathway. In cancer, several mRNAs are indicated to be involved in modulating the pathological processes and are considered an important target for anticancer therapies. Curcumin has been shown to exhibit an epigenetic regulatory effect on mRNA 131. A recent study in lung cancer cells showed that curcumin inhibited the enhancer of ZEST homolog 2, EZH2, coding mRNA expression through the upregulation of miR-LET7C and miR-101-124. Interestingly, many studies provide evidence of the EZH2 association with tumor malignancy and poor prognosis 125. Therefore, inhibiting EZH2 can be a potential target to treat lung cancers. Additionally, curcumin was found to upregulate the expression of miR9, with subsequent downregulation of the WNT/beta-catenin expression in oral squamous cell carcinoma cells 132. Aberrant WNT/beta-catenin pathway activation plays a critical role in tumorigenesis by altering cell cycle progression, cell survival, and invasion 132. Thus, by regulating the expression of miR9 and WNT/beta-catenin signaling pathways, curcumin inhibits the proliferation of oral squamous cell carcinoma, SCC9, cells 132. Moreover, miR31 is usually upregulated in oral squamous cell carcinoma, which can be due to the activation of epidermal growth factor, EGF. Surprisingly, treatment with curcumin reduced anite activation, leading to the attenuation of C/EP and suppression of miR31 upregulation in oral squamous cell carcinoma cells 133. Likewise, curcumin regulates the expression of miR7, which has been shown to suppress cell growth and proliferation, promote apoptosis in pancreatic cancer cells, and reduce histone lysine methyltransferase, SET8, expression, a target of miR7 134. Also, miR146A expression is reduced in pancreatic cancer samples as compared to healthy tissues. One of the miR146A targets is EGFR, and treating pancreatic cancer cells with difluorinated curcumin, CDF, resulted in the re-expression of miR-146A that led to the inhibition of tumor xenografts growth as well as decreased expression of EGFR, extracellular signal-regulated kinases, ERK1, ERK2, and Kirsten rat sarcoma viral oncogene homologue, CRAS. The miR-146A knockdown in the pancreatic ASPC1 cell line increased EGFR expression and enhanced clinogenic growth. Therefore, the inhibition of EGFR by upregulation of miR-146A through CDF treatment can be used to treat pancreatic cancer 135. These findings suggest that various mRNAs are great antineoplastic targets for curcumin. Furthermore, curcumin plays an essential role in gastric cancer by suppressing G1 to S phase transition during cell cycle progression 136. Cyclin D1 activity is crucial for cell proliferation and regulation during the cell cycle, and its degradation at the G1 phase will halt the cells from progressing to the S phase 137. In gastric cancer cell line, AGS, the synergistic effect of curcumin with doxorubicin, a chemotherapeutic agent, has been reported 138. This synergism has been shown to significantly reduce tumor spheroid formation, invasion, and migration compared to doxorubicin or curcumin alone 138. The effect of both compounds together caused caspase-9 and BAX upregulation and the downregulation of BCL2 expression 138. This implies that curcumin can ameliorate the doxorubicin drug resistance in chemotherapy treatment by increasing the doxorubicin efficacy. However, curcumin's limited efficacy in clinical investigations is attributed to its low solubility, high rate of metabolism, and poor bioavailability. The use of nanotechnology strategies may aid in overcoming obstacles and facilitating the translation of curcumin from the bench to the clinic. Advanced drug delivery of curcumin nanoformulations or nanomedicine, can leverage therapeutic effects by enhancing bioavailability and pharmacokinetics, increasing tumor binding, internalization, and targeting. The benefits of adopting these innovative drug delivery systems are immense, and they have been well studied 139, 140, 141, 142. 3 natural products as immunomodulators in cancer. The maintenance of immune system homeostasis is a key mechanism essential for the physiological stability of living organisms. Natural products participate in different innate and adaptive immunity processes and are important regulators of immune system function. Natural products and their derivatives with immunomodulatory characteristics are now being used as therapeutic agents against various types of cancer. Natural products are known to stimulate nonspecific innate immune responses in which the immune system mediators such as innate leukocytes, NK cells, eosinophils, basophils, mast cells, and phagocytic cells, neutrophils, macrophages, dendritic cells, provide defense against pathogens 143. The amplification of the innate immunity promotes effector innate immune responses such as immune cell infiltration, phagocytosis, and other cytotoxic mechanisms such as NK cell-mediated cytotoxicity that leads to tumor cell destruction 144. Fig 3. Besides activating the innate immune response, some of the natural compounds act as immunomodulatory agents and lead to the subsequent activation of the adaptive immune system. In adaptive immunity, the tumor antigens are recognized by T and B lymphocytes through cell surface antigen-specific receptors and lead to an enhanced humoral response and elimination of tumor cells by different mechanisms such as T-cell-mediated cancer cell death. Fig 3. Fig 3. Download high-res image, 414 KB. Download full-size image. Fig 3. Role of natural products in innate and adaptive immune responses. Natural products stimulate nonspecific innate responses that leads to the elimination of tumor cells by various mechanisms such as immune cell infiltration, phagocytosis, and NK cell-mediated cytotoxicity. Natural products also possess immunomodulatory properties that can cause the activation of the adaptive immune system leading to T-cell-mediated tumor cell death and enhanced humoral responses. NK, natural killer. Some of the well-known natural compounds in clinical trials that play an important role in immunomodulation in cancer are curcumin, Res, epigallocatechin 3-gallate, EGCG, quercetin, capsaicin, and genistein 145. The antioxidant properties of natural immunomodulatory compounds such as curcumin, res, quercetin, and genistein allow them to be used as a prophylaxis against tumor initiation and development. 146, 147, 148, 149. Naturally occurring immunomodulatory agents can prevent tumor propagation through cell cycle arrest and induction of apoptosis. 150, 151. Besides the well-known anti-cancer and anti-inflammatory effects of curcumin, studies have also reported the immunomodulatory effects of curcumin by regulating a diverse range of molecular targets. Curcumin has been reported to inhibit the accumulation of myeloid-derived suppressor cells, MDSCs, in the spleen, blood, and tumor tissues in a human gastric cancer xenograft and mouse colon cancer allograft model. 152. Moreover, in vivo studies have reported that curcumin enhances the cytotoxicity of CD8+ T cells towards tumors through the alteration of the tumor microenvironment, TME, when combined with adoptive therapy. 153. And also enhance the mitogen and antigen-induced proliferation potential of T cells. 154. On the other hand, residential is reported to exhibit immunomodulatory effects in various cancer models in vitro and in vivo by favoring tumor inhibitory cells in the TME and increasing immunogenicity. Check Review 155. In addition, residential and curcumin have also been shown to stimulate natural killer NK cell activation in YAC1 cells. 156. Among the flavonoids, flavones such as apigenin and luteolin are reported to exhibit immunomodulatory properties. 157. A study found flavonoids such as apigenin, luteolin, and quercetin to enhance NK cell-mediated cytotoxicity against lung cancer cells. 158. Moreover, the study reported that treatment with apigenin and luteolin increased the secretion levels of perforin and granulysin, cytolytic proteins stored inside NK cells, from NK cells. 158. Another naturally occurring flavonoid, genistein, has exhibited immunomodulatory effect by increasing lymphocyte proliferation in a cervical cancer mouse model. 159. Another study showed that treatment with genistein enhanced cytotoxic T cell, CTL, activity and enhanced IL-2 stimulated NK cell activity in B16F10 melanoma tumor cells in vivo and in vitro. 160. In another study, the combination of EGCG, the antioxidant component of the green tea, and DNA vaccination enhanced tumor-specific T-cell immune response in murine tumor models. 161. In vivo studies have also shown that treatment with EGCG promoted NK cell activity and increased T and B cell proliferation and enhanced NK cell-mediated cytotoxicity in a murine leukemia and bladder cancer model respectively. 162, 163. Alternatively, EGCG, the antioxidant component of green tea, has been reported to suppress the proliferation of peripheral blood mononuclear cells isolated from breast cancer patients and stimulated separately with mitogen, anti-CD3, and cancer antigen peptides, thus showing an immunosuppressive effect. 164. Treatment with capsaicin, an active component of chili peppers, has also been reported to enhance CTL activity in colon carcinoma cells and elicit a robust T-cell response in a meth-A fibrosarcoma tumor mice model. 165. Thus, the immunomodulatory characteristics of natural products, their extracts and derivatives can serve as efficient therapeutic targets to develop novel immunomodulatory agents to supplement chemotherapies which can help restore immune surveillance and target the complex immunosuppressive TME, the major obstacles in cancer therapeutics. For conclusion, the frequent occurrence of various cancer-causing genetic mutations leads to the failure of cancer management therapies, thereby making cancer prevention an exciting area of anti-cancer research. Due to increased research, the mechanisms of cancer's abnormal signal transduction pathways and their effects on carcinogenesis, apoptosis, and metastasis are becoming more clear. The quest for specific molecules that can influence signal transduction has recently become a popular biomedical research topic worldwide. One common theme that has emerged in all the studies comprising natural products is their tendency to target multiple oncogenic signaling pathways simultaneously by modulating the activity or expression, or both, of their molecular targets, affecting apoptotic cell death, cell proliferation, migration/invasion, angiogenesis, metastasis, and other pathways that are unique to certain natural products. The majority of natural products target intrinsic apoptotic signaling pathways, generating several intracellular signals that trigger mitochondrial-initiated events that lead to cancer cell death. Interestingly, natural products can be employed as adjuvants to improve the drug sensitization of chemoresistant cancers. Understanding oncogenes, anti-oncogenes, and their regulatory signaling pathways is required for the prospective use of natural substances combined with conventional treatment therapies. Natural products as chemoadjuvants are an active research area that must be treaded cautiously to produce the best treatment outcome in cancer patients. In the near future, a better knowledge of natural product targets and how they disrupt the oncogenic network in cancer cells in combination with existing therapeutic choices in different tumors by lowering drug-related toxicities will be a hot topic of research. The other research area regarding natural products that needs special attention in future is to improve their solubility, rate of metabolism, and bioavailability, and use of advanced drug delivery options such as various nanodelivery systems that include polymeric nanoparticles, lipid nanoparticles, liposomes, micelle, lipid nanoparticles, gold and silver nanoparticles, and silica nanoparticles may aid in overcoming these obstacles and facilitating their translation from the bench to the clinic. To summarize, the goal of this review is to draw scientists' and researchers' attention to the various beneficial effects of natural products in the development of new and safe drugs for possible cancer therapy, and it could serve as a strong foundation for more extensive research into natural compounds in cancer therapeutics. Author statement.